All right, everyone. We're still missing one committee member, but she's heard a little bit more about this than most of us, and we're really running late here. So it's my pleasure today to introduce Ming for his defense. As you're going to see, there's quite a bit that was done in here. I'm pretty happy about the sorts of developments that happened in this thesis, even if at the start Ming had no idea just where this would go. I guess not necessarily any of us did, but I'm glad that it came to where it is, and I'll let you show what it is.
Thank you, Nuno, for the introduction, and thank at least most of the committee for being here. But the title of today's talk will be, actually I don't remember it, Spectral Library Construction and Matching of MSMS Spectra at Repository Scales. And so I really just want to start off too thanking the committee and everybody I've interacted with throughout these 6+ years. Yeah, as Nuno mentioned, I was brand new to this a while ago. I had no idea what mass spectrometry was. I barely knew what bioinformatics was. And he didn't have much to work with, but he was a great mentor and advisor. And I'm actually very proud of the work that we've done together with most of the people in this room, actually. And it's been such a fun ride. And we'll share a little bit about what we did with the rest of you. So, you know, this is kind of a deep title. Let's take a step back. And one of the fundamental things that we want to answer is, what are the molecules around us in this world? What are the molecules on our skin? What are the molecules in our cells? How do these biological processes interact? And we want to start answering that question. If we can understand that question, we can really start getting at, you know, the mechanisms in our cells, and then that will allow us to have insights into disease, find biomarkers to diagnose disease, and also it's a way for us to discover new therapeutics. And so how do we start looking at these molecules around us? And one of the techniques that we've bought into is mass spectrometry. And so why mass spectrometry for this particular application? And one of the reasons is it's high throughput. We can look at tens of thousands of molecules in a typical experiment over a span of several minutes to an hour. And this is in contrast to other techniques that we're talking about, a couple compounds over a couple hours. So this is high throughput. It's quantitative. We can not only start asking what's there, but how much of it's there. And finally, it works on a broad category of different structures, from peptides, proteins, sugars, nucleic acids, metabolites, lipids. And so it's widely applicable. And so that's why we believe mass spectrometry is such a good analytical technique. And so just to give you a little background on the kind of data that we're looking at and what a mass spectrometer is, it's essentially a very fancy, very expensive scale. A scale that you use to measure the mass of molecules. And so, you know, you can weigh each of these molecules. It'll tell you it's however many Daltons. And that might tell you the number of nitrogens, the number of carbons, the number of hydrogens that are in that molecule. But that's not enough. We want to know how these molecules are actually arranged. And that tells us information about how it can interact with the rest of the system, the rest of the world, the chemistry. And so what we can do to start getting at the structure is we can break it up. Some of the bonds in these molecules are stronger and weaker than others. And what we call tandem mass spectrometry takes advantage of that. When we fragment these molecules, the weaker bonds will break first. And then once we break it up, we measure how much the pieces weigh and how much of each piece is actually there. And this gives us a somewhat unique signature of that particular molecule. And so now we've taken a biological sample, we've analyzed all the molecules in there, we've broken them up, and we see these signatures. And we want to answer the question of what's actually in our sample, what molecules are actually in our sample. And so we have to infer that what molecule gave rise to this spectrum. And one of the core components in answering this question is you have to be able to predict the fragmentation given a structure. And so the problem is, in a lot of classes of compounds, this is actually really difficult. There's no generalized way for us to guess at how it'll break up. And even in the cases where we do have a much better handle, such as proteomics and for peptides, we do have a good guess, it's not as accurate as actually observing the real thing. And so we decided to take another approach at this. Well, if we've seen a compound, or seen a spectrum for a compound, and we've identified it, let's remember that you cannot do better than the actual fragmentation. You can't guess better than that. And so that's what spectral libraries are. They're collections of spectra where we know the annotation, and they're lumped together into this corpus of knowledge of what we know. And so to actually identify new spectra, new compounds in a sample, if we have a bunch of these query spectra that we have no idea what the identity is, we can compare them to library spectra, and if they are similar, then we can do an annotation transfer from the library spectrum, because we know what the library spectrum is, and say, look, in your sample, this spectrum is this structure. And so there's two key components to this particular procedure. You want to be able to answer the question, given two spectra, how similar are they? And are they sufficiently similar for us to say that they're the same compound? That's spectral matching. And the second component is that the library has to be complete. The libraries have to be complete. If you have nothing in your library, you have nothing to compare against. And so that's what we'll be talking about today. First, how do we assess the similarity of MSMS spectra, and how do we assign significance to that? And also, how do we start building spectral libraries in a scalable and an error-controlled way? Okay, so let's get started on the first point, on spectral matching. And just to give you a little background, how the field has centralized on assessing how if two spectra look the same, we have this thing called a cosine score. And then the way we approach this is each spectrum, on the x-axis is the masses, and the y-axis is the intensity. We treat each spectrum as an n-dimensional vector, where each dimension is the mass, and the magnitude in each dimension is the intensity for that given mass. And now to say that if they're similar or not, we have both of these vectors in an n-dimensional space. We can measure the angle between them. And then you can take the cosine of that angle. And so if they're exactly the same, the vectors will be right on top of each other. If they're completely different, they'll be orthogonal to each other. And so if you take the cosine of that angle and you get a number out, 0 means they're completely dissimilar, and 1 means they're completely identical. But one of the problems with this cosine score is that the actual number might not be indicative of the reliability of the match. So let me just ask you this question. So we have this library and query on the left side, your left side. And they share only one peak in common. The other small peaks don't actually match. But on the right side here, all three of the peaks in the library and the query spectrum match. Which one do you believe is to be more confident to be correct of a match? Any guesses? Andrew?
The one on the right.
That's what I would think too. But the problem is, both of these have the exact same cosine score. But this one on the right, we believe, is more correct. And so we want to account for that. We want to assign significance to these matches. And perhaps some library spectra, some spectra in general, are much, much easier to match with a high cosine score than others. And so Nuno and I, we worked on this problem, and we came up with a solution called the spectral library generating function. So it's a mouthful, but just very, very high level. If we want to assign significance, generally the null hypothesis in finding p-values for scores, you want to assume that your new query coming in is random. It's a random spectrum. And so you ask, what is the distribution of scores between my library spectrum and all random spectra out there? And that's modeled here in red, and that's the traditional way of doing it. Unfortunately, for library matches, we can't estimate this distribution, this red distribution, both analytically or empirically. We can't do it analytically because we have to have the notion of what a random spectrum coming out of the mass spectrometer is, and we have no good model for that. How do we generate them that they look faithful to real spectra, but they're not actually real compounds? Second, we do have a large corpus of data, but it's not large enough. We have billions of spectra, but that does not we can estimate the body of this distribution, but what really matters is this tail right here. And you need so much data to estimate that tail, and you need to estimate that tail for every single library spectrum. It's just too computationally intensive. Instead, we flip the question. We change the null hypothesis and say, well, we can't find this red distribution, but what if we assume that the query spectrum is actually a replicate or from the same compound as our library spectrum? We acquire the same compound multiple times and see how it looks compared to the library spectrum. How much variability is there in the mass spectrometer when we acquire the same compound multiple times? And so we can actually calculate this distribution here on the right. And once you have this distribution, you can ask the question, well, if I have a new query that matches the library, do we expect it to look, how reasonable does it look as a replicate spectrum? And if it's a low score, we're like, oh man, we wouldn't expect a replicate to look like this very often. And so we can calculate a significance for that match. And the way we go about this is we quantify peak intensity variability. And the reason these peak intensities vary if you shoot the same molecule into your mass spectrometer is because of the stochasticity of fragmentation as well as instrument measurement noise and error. And so we're capturing that here. For every library spectrum, we look at the same peak in replicate spectrum and see how much it varies. And once you do this enough, we find if it's a very low intensity peak, it will vary quite a bit, so shown here in red. And that's to be expected. Just because it's low intensity, it's more influenced by noise. But if it's high intensity, it doesn't vary very much because it's not as affected by noise. And so now we understand the variability of a single peak in the library spectrum. And then we can generalize that across all peaks in the library spectrum. And so with that notion, we can start exploring all possible replicate spectra that could arise from shooting that same compound at the mass spectrometer. And then if you explore all replicate spectra, you also have an understanding of how likely it is to occur because you know how likely it is for each of those peaks to vary by a certain delta. And then we can explore all possible replicate spectra of a library compound. And then we can ask the question of how similar those replicates are to the library spectrum. And we solve this with a dynamic programming approach. And the running time is linear to the number of peaks in the spectrum. And we actually applied this to a large couple 100,000 spectral library. So it's very computationally tractable. And what we end up with is a distribution of scores between a library spectrum and its replicates. And what we can do is we can rescore a spectrum match between a query and a library. If we have a score T here, it's simply the integration to the left of this point. And from the specific example that we saw earlier, where it was just one big peak, it has a cosine of 0.8. We know that this very intense peak shouldn't vary very much because it's very intense. And so we would expect all the replicates of the library spectrum up here on the right to have a very high similarity to the library spectrum, all the replicates to have a high similarity to the library spectrum. And then when we rescore it with this SLGF distribution, we find it has a score of 0, and we don't believe it. And when we apply this to actually identifying spectra in samples, we can find here, at a 1% false discovery rate, we fix the specificity. We can find that our tool, called that SLGF approach, in rescoring these scores with significance, increases the sensitivity over the state-of-the-art library search tool that is more or less cosine-based by 16%. And so we've taken the step into making spectral library search more sensitive. So now the other half of the puzzle is, where do these libraries come from? And so one particular space that we targeted, oh, go ahead.
Sorry, a quick clarification question.
Yep.
Do the spectra for a given compound, do they vary even in terms of which peaks occur? Like, for example, could some elements not get detected? Or is it purely only the intensity of each of those peaks?
So in some cases, they are deleted. And if it's low intensity, it might not pick it up. If there's just low intensity, it might get lost in the noise. So that's something we do model that we glossed over here. We did not model peak insertions. If the library spectrum, for whatever reason, are missing some peaks, we don't model the insertion of peaks in a replicate spectrum. But excellent question. And feel free to ask. Don't be shy. Don't be shy. And so we're going back to natural product libraries. And one of the reasons these are important is for natural products is a fertile source for therapeutic compounds. Things like penicillin are natural products. And if we want to discover something new in the natural product world, we have to know what already exists. And so one of the ways to capture what already exists is through libraries. And so in typical natural products experiments, and you analyze with a mass spectrometer and you get these tandem mass spectra out, you get less than 1% of the spectra being identified. That's pathetic. And so you might wonder, well, why? Is the data bad? And I will show a little bit later and explain a little bit later, no, the data is not bad. We see consistent and correlated signal in the data. That means these are real compounds. And maybe spectral library search is insensitive, but we've taken steps to ameliorate that particular problem. And so the last point is maybe the libraries are incomplete. And so we're going to tackle that here. And so in the natural product space, there's a huge diversity of possible structures that can occur. And there are tools out there, there's computational tools that take a particular spectrum and try to identify it to a database of structures. So essentially they try to simulate the fragmentation of these structures and match them to an unknown spectrum. Unfortunately, these approaches, because we don't understand fragmentation, we can't accurately predict fragmentation, it yields high error rates, as well as excruciatingly slow identification rates, or identification in general. So it's not really high throughput, you can't really automate and trust what comes out. You have to do some manual validation. And there are alternate ways where we can get unambiguous identification of the particular structure, such as nuclear magnetic resonance. Unfortunately, this is not really high throughput either. We're talking about you have to grow enough of the particular bug or organism that's producing the compound, purify the particular compound, and then stick it into an NMR, and you have to solve the structure. This can take months of effort for a graduate student.
Years.
Years for some.
No, not for some.
For all?
There are some decades.
Well, people in your lab seem to do it pretty quickly, so I take that as the benchmark. So either months or years, it doesn't compare to seconds. So, but there are some structures, there's sometimes some molecules, you just have to do it once. You have to. But let's make sure we only do it once. We don't repeat something in 2017 that was solved in 1970. And so every time somebody puts this, spends all this effort in identifying a particular molecule, let's remember that. Let's let the community contribute and remember that. And together with Peter, Nuno, Vanessa, Laura, Yao, Jeremy, and then 120 other authors, we worked together to create this platform called GMPS. This platform allows the crowdsourcing of these spectral libraries. If a scientist out there in the world spent months or years identifying a compound they really care about, let them share that with the world. And to date, we've had about 19,000 MSMS spectra from nearly 11,000 compounds, and 91 contributors add to this library resource. And so whenever we were developing this, the things that we had to think about are how do we actually motivate the community to add to this resource? What makes it worth their while? And how can we create a benefit and cost structure that convinces them to be a part of the system? And how do we make sure, and how can we test whether what they added was of high quality? And to address the first point, to convince members of the community that this is worth their time, we want to increase the benefit. And the way we do that is, if you upload your particular spectrum for a compound today, you can take all of your data and re-identify that same compound today. In addition to that, we search all the public data automatically. And so if a user uploads a particular compound, we'll be able to tell them, look, this also occurs in this data set, this data set, this data set. So we automatically amplify the benefit of adding a single compound to the library. And to reduce costs, we try to make a user-friendly interface for that to happen, and easy ways to upload lots of compounds at a time. And when we look at the utility of the library compounds that the community uploaded, we can see from the community and also from Peter's lab, they identified over 80% of the spectra in people's data, in real experimental data. And so it's been shown to be immensely useful. And not only that, this is surprising because the GMPS libraries are only about 19,000 spectra, whereas the existing libraries are currently 10 times larger, about 200,000 spectra, but they identified less than 20% of the data. So we can see here that the GMPS community is uploading spectra that matter, uploading compounds that matter and actually occur in real data. And so it is disproportionately useful to its size. And so now the next question is, how reliable are the spectra? And the way we started getting at this is, well, we make identifications with these libraries. If they don't make good identifications, that's cause for concern. And so when we make identifications, we ask users, was this right? And they can answer, yeah, it was correct. I'm unsure. It's actually a structural analog, or it's completely wrong. And when we compare the answers that users gave compared to existing libraries such as the National Institute of Standards and Technology and other third-party such as MassBank, we find that the libraries uploaded by the community is at least as reliable as these state-of-the-art resources out there. So this gives us confidence that we're not doing any worse, at least. And one of the really cool benefits, we think, of the GMPS system and why the community is really, really necessary is that if you sat in a hole, you had your own little lab, you uploaded compounds to your own private database to identify compounds, you would get some number of identifications to your data. But now that we have the community engaged and adding to this community resource, that increases your identification rates by 5x. And who doesn't want that? And we've been lucky in a way that the community really has taken hold and they're using the system and contributing. And to date, I think these numbers we are with the paper, so they're kind of outdated, but over 100 countries, I think 20,000 users nowadays, 40,000 sessions, 1 million LCMS runs analyzed, and several billion spectra. It's just to give you an idea of how useful these libraries have become. Yeah?
So the library, each data point is just like a 1D function where at each mass you have the percent or whatever?
Yes,
so
yes.
It's a pretty small amount of data.
It is pretty small, yes.
And then how do you get like poor would that be because the person was not actually a scientist and uploading garbage, or they executed the experiment wrong, or their machine was just faulty, or? So
they could have made an error as an uploader that this particular spectrum is not what they thought. They could have uploaded that it's actually correct, but it's low signal to noise. So there was low abundance, so there's just a lot of extra noise around it. So those are two possible causes of error. Or they're just completely wrong. They just give you the wrong identification. They're malicious. But we have not seen much evidence of that. But what we have seen are a couple hundred, I'd say 600 or 700 I've encountered recently, corrections to annotations in the library. And this can range from, because of their incorrect assignments, which is a small percentage, and also adding extra metadata to actually enrich the identification. Questions? Okay, so that's where we built these libraries, we made them bigger, we increased the identification rate of libraries by 3 times. You can have a seat up here. We increased the identification rate of these natural product data sets by 3x, from about 0.6% to 2%. That still sucks. 2%, 98% of your data is going to waste. So we implemented some new techniques to try and expand that. And so the thing is, well, we only can identify 2% of the data exactly. But what if we can not identify everything exactly, but give a hint at the rest of the data, at what potential structure it could be, or some parts of the structure? And so what we can do, and we'll show in just a second, is we can get 10% of the data, so 5 times more data with a hint at the structure. And the way we do this is creating molecular networks. And I'll just give you a taste of how we create these molecular networks from the bottom up. And so now if you imagine 2 compounds, they differ by a small modification. In this example, this delta here. So, and if they differ by that, and it doesn't really change the strength of the bonds in this particular molecule, and you put both these compounds into a mass spectrometer, they should fragment very similarly. Except some of the fragments, some of the pieces in the second molecule with this delta will weigh slightly more. It'll weigh the mass. The change in mass is actually the mass of exactly that delta. And so we can take advantage of this notion. And we can start aligning 2 spectra that might differ by a single small modification such as this. And so applying this to toy spectra here, we have this molecule, the spectrum for this hypothetical molecule on top, and the spectrum for this second molecule with a delta on the bottom. And so some of these peaks could have shifted by a delta, and some could have stayed the same because they didn't have the actual delta on the pieces. And so you can think of all the possible choices you can make. For each spectrum on top, you can say, well, let's match at the same mass. Let's match the same mass. Let's match at a delta. Let's match at the same mass. And in this particular case, there are 4 possibilities of alignment. And we can enumerate, we can go through all these possible alignments and pick the alignment such that it maximizes the similarity between these 2 spectra. And if it exceeds some score thresholds, which we view as reliable, we can say, look, these 2 compounds are likely to be structural analogs. And so if you do this on a per spectrum basis across all the spectra in your data set, what you can end up with is a molecular network, where each circle here, each node here represents a spectrum, and each connection represents a guess that these are structural analogs. Yeah, Bahar.
How do you choose your delta? Are they just the most prevalent modifications, or how do you choose the list?
So the delta is chosen because we actually know the full mass of this molecule. We first weigh the molecule. Exactly, based on the precursor. And so now we've organized it into families of molecules. And so we saw before only 2% of the data were identified. But if we know that every molecule in a particular family and in a particular connected component, they're structurally related. If you have an identification of just one molecule within that family, that gives you information. It gives you a hint at the structure of everything else in that family. And so what we start off with is 2% of the molecules being identified. But now, if we look at the molecular families that have at least one identification, which gives us a hint at the structure, we expand that to another 10% of the data. And then beyond that, 25% of the data includes molecules and spectrum molecules in families that have no identifications. But all we need is a single one to give us a hint. And so this gives us another way to incentivize the community. If they upload a spectrum that's completely novel chemistry that didn't exist in our library before, they have the possibility of not just identifying one more molecule again, but assigning putative structures to 25% of the data. And so just to give you an idea of how GMPS and these tools have been applied, we worked with Amina and a lot of other people and from Peter's group to have a molecular map of the skin microbiome. We also used GMPS to discover a novel analog of stenothricin with cool bioactivity. And also the libraries were used by other computational groups to actually learn more about fragmentation. Because we have the spectra and the annotations, we have thousands, tens of thousands of molecules, it allows them to get insight to learn about how to predict fragmentation better. So in the future, we can hopefully these tools evolve. And so that's some of the benefits and applications of this GMPS platform. Okay, so we're done talking about natural products for now. And another space that we targeted is proteomics. So the study, the identification, quantification of proteins. And so proteins, they're in your cells. And they're like cytoskeleton, they're enzymes, so they are the functional aspects of your cells. And so it's important for us to be able to measure and capture that. And with spectral libraries, they provide a sensitive way to identify these molecules in a sample. And in difference from the natural product space, for proteomics, we actually are able, or much more able, to understand the fragmentation of peptides. So we can actually predict them. And so there exist computational tools where we can reliably identify peptides in actual mass spectrometry data. But the downside is current libraries out there, they're small. They don't cover a lot of the human proteome. Out of nearly 20,000 proteins in the human proteome, only 12,000, 13,000 have any unique peptides that map to them. And the National Institute of Standards and Technology, NIST for short, they provide a peptide spectral library. And this is what a lot of the community currently uses. Unfortunately, it lacks coverage. It covers in the 26% of the full proteome. So it misses a lot of the amino acids in the proteome. And you might say, well, who cares? If we have the proteins, that's all that matters. But that's not all that matters. There's a lot of active sites that are not captured by the peptides in these libraries. And if you don't have these peptides that capture these active sites, you don't know how to go quantify them, you don't know how to even find them. And so we need to start expanding our spectral library so we cover more of the proteome and we cover more of the functional proteome. And one of these other missing points in the existing spectral library, specifically NIST, we do have no idea where what files created them, how do they actually create this library. And if we're using spectral libraries as a reference set of known compounds, of high quality known compounds, if you don't know how they got to that point, that's a huge missing piece. You can't trace back to what metadata, to what files, what tools, what search parameters, or even to visualize what is there. So you can't really use it as a confirmation step. And so we ventured to build a spectral library that is more comprehensive, that has all this provenance information, and has proper error controls. So if we're using it as a reference set, we can trust that it really is a reference set. And so to start off with, you need a lot of data. You need a lot of data. And so just to give you an example, there is a mass spectrometry repository in the UK called PRIDE. And it houses about 86 terabytes, approximately 88,000 LCMS runs of human proteomics data. And another thing that you need is identifications into this data. Unfortunately, 86% of the data has no identifications. It's worthless to us right now. And that chisels it down to 11.5 terabytes. Beyond that, half of the identifications don't even tell us which spectrum in the sample it is. So that's worthless. And then another half, the error rates that are for the identifications are unknown or are too high. So those aren't useful to us either. So at the end, out of this 86 terabytes, we only have 3 terabytes of usable data and 15 million spectra that were identified. Let's fix this situation. We're missing, this is about 5% of the data. We want to use all of it, or as much as possible. And so we ventured, so actually, one of the things we have here at UCSD that's run by Nuno, Pavel, and Vineet is the Center for Computational Mass Spectrometry. And we have started what we call the mass spec interactive virtual, okay, it's a mass spectrometry repository. I've never said this out loud. But anyway, so it's a mass spectrometry data repository that specializes in reanalysis. There's so much data out there. One of the things that specializes is data reanalysis. There's so much data out there with no identifications. It's not really reusable for the community, and we want to fix that. And so part of this massive data repository is that we can users in the community can deposit data. We can pull in data from other repositories. We can convert these proprietary formats to open formats. And we also can do automated reanalysis. Further, we index all these reanalyses for users to actually explore these identifications and reuse the data. And also have advanced analysis tools to allow the community to really explore the data in depth. And so when we built this platform to enable the creation of spectral libraries, there were a lot of engineering challenges that went into this. And it's a lot of these things seem mundane, but if you're really deep into it, these things matter. And so conversion to open formats. Generally, all these submissions are in proprietary formats that are not open, that tools cannot actually read. So we have to make sure everything's open, everything's converted. Beyond that, to do proper reanalysis of data on this scale, we need a lot of compute. We're talking about hundreds of CPU years of compute, which is out of the reach of most laboratories out there. We need robust analysis workflows. We need things that can analyze data on this scale, that don't eat up RAM, that is high throughput, and that can tolerate failure. And we also need to be able to track provenance. Whenever we analyze something, we must be able to go back to the original data, to the original job, the original parameters. And we also need to visualize what we're actually observing. And so all these things together help to make Massive what it is. And we actually took a bunch of this data. We took almost all of the human HCD data. So this is a particular fragmentation type. And that's about 31 terabytes that we reanalyzed. And this is about 85% of the total out there. And this is about 34,000 LCMS runs, a little over 500 million MSMS spectra. And we searched it with a tool out there, a database tool, that allowed us to assign identifications to all these spectra, peptide identifications of these spectra. And just for using this one tool, it was slightly over 100 CPU years of time. And at the end, we end up with 208 million spectra that are identified. And the problem is, we could take these identifications, put them all together and say, hey, we have a library, and do that naively. Unfortunately, you can't do this. If you, at this scale, if you naively start combining identification results, what you end up with is a huge mess. We want this library to be a reference set. But if you combine it naively, 28% of the compounds that you're seeing, of the peptides in this library, they're wrong. That's an unacceptably high error rate. You can't refer to this as a resource for the community.
Question?
Yes.
If you would only combine this library from 0% FDR identifications, would it still be high percentage of erroneous identification?
So you wouldn't know. So whenever if you do local FDR, or you do FDR on a per search basis, and then you combine them, you will as you keep scaling out to more and more searches, the error is going to keep growing. But you don't know the error.
I'm not talking about local FDR. I'm talking about only reporting PSMs with zero FDR, which means PSM is p-values that are below of any p-value in the decoy.
If you do this globally, I imagine you might be okay. But you have to do it appropriately, because if you do it on the PSM basis, you might still be screwed at the precursor basis. Because you might have, if you will still have some error, there's going to be something wrong. But if you have it at the PSM level and then you aggregate at the precursor peptide level, all the true identifications will, they'll all line up. All the false ones won't. They'll splay out. And so you're going to end up with high error rates, or an unknown error rate. And you need to start controlling that. So you can set some bar, but that bar won't be appropriate at all scales.
I don't understand it. So if we believe into FDR, that at 0% FDR, you presumably have no false identifications.
So
if you combine many data sets in which of them there is no false identification, then presumably you have a kind of golden library. You, in the case of PNP, you assign kind of quality sign to each PSM. And in this case, it would be some equivalent of the quality sign.
So if you could truly get 0% FDR, that's great. But there's always going to be some error in there. Do you believe that you can actually truly get 0 error?
I mean, of course you cannot get 0% FDR in series, but in the existing approach to FDR identification, you can formally talk about 0% FDR. So
there's this trade-off between sensitivity and specificity. If we start sliding the scale all the way towards 0% FDR, it's going to cost you a significant amount in terms of sensitivity. So you can do this, but then your library is going to be significantly smaller. So when we talk about these ROC curves for FDR and number of things that are identified, you kind of want to be at the knee of the curve. If we slide it all the way over, your library is going to be puny. So you can do this, and if you can truly get 0% FDR, that's great. But then your library is going to be a quarter the size or even smaller than that. And then it's not really useful for the community because it doesn't cover very much. Are you convinced, Pavel?
Yes.
I would actually add that you can't get 0% FDR. You can get an estimation error.
Yes, of course.
You just don't have enough decoys to know how much larger than 0 it is. But that's an estimation error.
If people proudly publish list of identification with 1% FDR, somebody can equally proudly publish a list of identification with 0% FDR.
But the error
not true, because the variance of the two estimates is not the same. Because with 1%, you have an approximation from the number of decoys, but 0, there's no decoys, there's no estimate, right? So your error is actually going to be worse if you claim it's 0.
Don't be shy if you're not convinced, Pavel.
I'm not convinced, because in the end you can combine all spectra into a single data set, run image plus on them, and set up whatever threshold you like on this data set, let's say 1%, and then declare your spectral library to have 1% false identification.
Well, that's what we eventually do. There's other things we do, but let's move on, and we'll come back to this. Okay, so we need to control error in these libraries, and so there's several possibilities, several ways to start attacking the error, and one of the ways is we want to make sure that higher scoring spectra, or better quality spectra, more reliable spectra, have better scores. And so that's actually handled by MSGF plus the spectral probabilities. And so if there is a better spectrum for a given peptide, that'll lead to a better score. If there's a better peptide, there's a better explanation for the fragmentation we're observing in a particular spectrum, you'll have a better score. And further, to be able to have the confidence, the reliability of the score of an identification should reflect first, the quality, how well the data within one particular spectrum is explained by a peptide. And number 2, it should also have the reliability of the metadata. If we synthesize a peptide, we should have a lot of confidence of what we're observing in that particular spectrum is actually that peptide, because that's the only thing that went into the mass spectrometer. As opposed to if you took a whole cell and you found one peptide, you'd be a little less confident. And so we'll talk about how we address the second point in a second. And also, we will need to address library level FDR. Once you put everything together, how do we start controlling for the error when we have so much data together? And because all the true identification, the good spectra and the good peptides that are observed many, many, many times, they'll still be observed many, many, many times correctly. But all the false identifications are randomly splayed out. And so if you do not control this appropriately, you can have an unacceptably high false discovery rate in your particular library. And so here we'll talk about how do we account for the search space appropriately. How do we have a score that first reflects the quality of a peptide spectrum match? How well is the data explained by a particular spectrum? And how can we work in the confidence of the search space? If it's synthetic, we should trust it more. If it's a full proteome, full cell lysate, we should trust it a little bit less. And so what we do here is we borrow a notion from Nitin Gupta, and it's called a database search p-value. And so here's our expression. So we can break this down a little bit. And so this term in the middle, which this p of the spectrum given a score t, imagine you have a particular peptide and a particular spectrum, and they have some score t. They match whatever algorithm you're using. And then this term here is the spectral probability, and that tells us the probability of a random peptide matching with higher score than t. So this is an error rate. And so lower is better. If it's all the way down to 0, there are no better peptides to explain it. And this captures the quality of a peptide explaining all the data in a spectrum. Additionally, we have this exponent here, n, which accounts for the size of the database. How many options are we trying out? For a particular spectrum, we try out peptide A, peptide B, peptide C. And so if in this middle term, without the n, we do 1 minus the spectral probability. That tells us the likelihood of a random peptide having a low score. And then if we raise this to the n power, because we ask the question about n particular peptides for that spectrum, how likely is it that all peptides that match to, or all random peptides that match to this particular spectrum have a low score? And then if we take 1 from that particular value, that will give us the probability of at least finding one random match with a high score. And so this is the error. This is how, the lower this value is, lower this score is, the more we trust the identification being made. And so this takes into account the quality of the match as well as the search space we're considering. And so how do we actually lower this score and make our confidence higher? The first way is you find higher quality spectra. If the spectrum is higher quality, it makes our spectral probability better, and it lowers, it increases our confidence in identification. You can also reduce the search space. If it's a synthetic peptide, there's only one possibility, and your confidence is reflected at this exponent here, will increase the confidence that you believe the identification. And so we use this concept as the primary score ranking for identifications. And we wonder how much improvement is there based on different search spaces. And so a lot of experiments out there are just full cell lysates. You throw everything into your mass spectrometer and you see what you get. So it's mostly the full proteome. And we see, okay, if it's a full proteome, it increases, this is a negative log, this is a log 10 increase in score. So the further you move, the more trustworthy your identifications are. And so for a full cell lysate, it doesn't improve that much because there's tons of proteins there. However, if you do certain things that constrain the proteome, that pull down only specific proteins, it increases the reliability by an order of magnitude. Further, if you synthesize a peptide, it pushes another order of magnitude in trustworthiness. And so now, instead of naively scoring your spectrum against the full proteome and incorrectly assessing the trustworthiness, the reliability of the identifications, here, if we adjust for the search spaces appropriately, we can capture the true reliability of these identifications. And so also beyond that, the need to control for global FDR, if we don't control these error rates, we end up with 28% of the library entries being wrong. But now what we do is control it at a 1% local FDR, and that yields about a 0.1% global FDR. So the library that we end up with is about 2.1 million precursors, but only 2,000 of them are wrong, estimated to be wrong. And we also apply a 1% protein FDR. So we reduce it from 28% to 0.1%, but at a sensitivity loss about half. And so now that we know what's going to go in our library, what particular molecules are going to be in our library, we have to choose which particular spectrum, because we observe, for a given molecule, we observe many, many replicates of many observations of that particular peptide. Which specific spectrum is going to represent that particular molecule? And so there's several ways to do it, but we need an external check as to how well are we doing. And the way we go about this is we take advantage of a certain type of experiment out there, and it's called SILAC. And what will happen is you have the normal peptide, but then you also have a variant of it that's heavier, that's slightly heavier. And we know how much heavier it should be. And then what'll happen is it adds a certain mass on the N-terminus of the particular peptide, and it'll shift the fragmentation just a little bit. But the relative intensities will be preserved. And so we take this data, we identify with a database search engine, we cut at an appropriate FDR value for identifications, and we look at concordance between these light and heavy pairs. And if you find that the concordance is defined that the light and heavy pair have the same identification, and the specific spectra also have high similarity in fragmentation, we believe that will reduce a lot of the error in this particular library. And what happened in applying this, we took 2.6 million MSMS spectra, applied these procedures, and came out with a gold standard library that has 29,000 precursors. And we use this as an external reference to check how well we are doing. And so now we have this external reference, we can go about picking the representative spectrum for each molecule in our library. And the procedure that we do is for each molecule, we find the top 100 best scoring spectrum for that particular precursor. And then we find the one spectrum in there that is most similar to all others. And so you're going to think an easy way is, why don't we always choose the highest scoring? But that might not be the best, because we think downstream we want to identify unknown spectra, and so we feel that choosing the most similar to all spectra will best aid in that. And whenever we compare these two strategies of choosing the best score versus choosing the most similar, we find that this distribution in yellow here is the score distribution between our gold standard and choosing the best score. But if we choose the most similar, we actually improve slightly on that. And now we can ask the question, how well is our library construction procedure compared to the state-of-the-art NIST peptide spectral libraries? And so here we have, in this distribution, it is the score distribution between the light variant and the heavy variant in the SILAC data, which we think is as good as you can do. The similarity between high-quality library spectra should be this distribution. This is as good as you can do. And so if we compare the gold standard library to NIST, we can see it's right there. So NIST is doing a reasonably good job of picking representative spectra. And see, we'll have a slightly longer tail, but the massive distribution is right on. And then finally, if we compare the massive knowledge-based spectral library to the gold standard library, we can see we're also in that regime without the tail. So this gives us confidence that this actual spectrum that we're choosing to put in our library is of high quality and is correct. And so once we took all this 31 terabytes of data and distilled it down into 2.1 million precursors into a spectral library, this is what we end up with. With NIST, we had about 496,000 precursors, and now we are 4 times larger at 2.1 million. And what's interesting, too, is the number of proteins we start capturing. NIST, at best, was capturing 13,000. But as we move we move here, without synthetic data, we're capturing 16,800. And with synthetic data, we're capturing 19,600, which is nearly all human proteins out there. And just highlight, in graphical form, we're increasing precursors by 4 times, sequences by 3 times, and coverage of the proteome by 2x. And similarly, this 2x increase in coverage of amino acids allows us to increase the coverage of active sites by 60%. And so we're not done. We still have about nearly 5 million more amino acids to cover that we haven't seen in the data. But we started from over here at 3 million, which is about 27%, and now we're over 50%. So that's a huge jump. And one of the things we built into our system is we're never done. Data is continually being generated by labs, being published. And as part of our procedure, anytime something is made available, we acquire it, we convert it, we search it, and we incorporate it into the library. As the community continues to acquire more data, so does the massive knowledge base. And one other thing we'd like to highlight is in this massive knowledge base, it identifies, without the synthetics, 16,800 proteins. The thing is, there are resources out there that catalog all the proteins that have ever been observed in real data. There's about 3,500 that have never been observed in real data with mass spectrometry proteomics evidence. But in our library, we actually observe 723 proteins that haven't been claimed to have been observed before. And these 723 proteins, they have at least 2 non-overlapping sequences that map to it. So that gives us a lot of confidence that they're real. But we want to further validate this. And 649 of them have previously had transcriptomic evidence. That gives us a little more confidence. 32 have homology, were predicted by homology. Another 12 were just predicted, and 30 were uncertain. But we want to further validate the things that we're observing. And so what we did was, for all the precursors that actually claim these 723 proteins, we compared it against synthetics. And when we compared it against synthetics, we compared how the spectra looked. And if the spectra looked the same, that gives us confidence that what we're actually observing in the data is real. And we can see here the score distribution between the items in our library and the synthetic data, how similar the spectrum are. And it's very tight above at a very high cosine, so that gives us a lot of confidence. These 700 proteins that we're calling, they're likely to be correct. About 70% of them were actually validated. The rest were not validated because they did not actually synthesize the correct proteins correct peptides that we're actually observing in the data. And so this is highlighting the size of the libraries. And that's great and all. But one of the uses of a spectral library is an identification. If we don't actually identify anymore, who cares? And so whenever we actually take the spectral library that we've generated, the massive knowledge-based library, and we search it against real data, in this case, we search it against a HEC293 cell line with about 1 million spectra, and we filtered the results down to 1% precursor level FDR. With the existing state-of-the-art library from NIST, we see about 77,000 precursors identified. But if we use the new massive KB library, we see 137,000 precursors identified, an increase of 77%. But where did this 77% come from? 60,000 of these new precursors did not exist in the original NIST spectral library. And so the fact that we grew the spectral library by 4 times, that made a significant effect on identification rates of this particular data. And so we hope that trend also continues whenever people use our library. And so just to give you a recap of all the things that we think people can do with these libraries. So we have this massive KB library here. Researchers can download the library. and do whatever they will with it to search on their own machines. They can even use it at the Center for Computational Mass Spectrometry and analyze their data through our web portal. And also, this massive KB, because it has provenance, it tells us what data, what search it came from, what tool, what parameters, what data set, and what specific spectra gave rise to it. It allows users to trace all this information back. And so if you made a discovery, something unexpected in your data, you can ask if the rest of the community also had the same observations. Beyond that, because we have full provenance of all the searches and how everything was added together, it empowers the community to reuse that information. They can customize how to analyze the data with new tools, different parameters, and they can reuse the exact same open library construction procedures to create their own boutique knowledge bases and libraries that they can use to download and search however they please. And so just give a quick overview of everything we talked about today. We started off asking, okay, given a spectral library, a reference spectrum, and something unknown, how do we say that these two are the same compound? So we assessed spectral matching significance. After that, we talked about, well, natural product libraries are small, they don't identify very much. How can we expand beyond that? And we've seen how the community has really bought in and has created a resource that's immensely useful. And we also did the same thing. We created libraries for proteomics data. And we've increased the size of the libraries by 4x and doubled the coverage of the proteome. And so I guess it doesn't seem like we did much in the past six years by putting it all on one slide, but it's been fun at least. But I want to just take a moment to thank everybody that I, professionally, socially, personally, that I've run into, I guess my whole life. But these are some of the people, and I'm sure I've left tons of people out. But thank you for listening. Thank you for being such an attentive audience. And I'd love to take any questions now.
So you used the cosine sort to measure distances between these distributions. Do you think about any other metrics, such as like Earth mover's distance?
Oh, the Manhattan distance?
Earth mover's distance?
What is that?
It is for measuring distance between distributions, but it's basically, if you think about these as piles of dirt, it's how much effort you have to do to move the dirt from one pile to another. So
It is very similar to Manhattan distance, no?
Isn't that just like the distance?
It's the...
Yeah. No, it takes into account the fact that if you have two peaks very close to each other, in your cosine metric, they'd be totally orthogonal because it's all, like, they're two separate bins.
Mm-hmm.
But in the Earth mover's distance, it's a very small distance.
Oh, okay. So that's a good idea. In general, because we have an idea of instrument accuracy, so if we're matching two spectra and then you want to move one peak to a neighboring bin, since we can adjust the bins according to the instrument accuracy, so we do not have to account for that. But there are other similarity metrics that were tried throughout the 90s, such as like Manhattan distance and more recently, like some hypergeometric functions, but it seemed like they were worse or at least at best on par with cosine-based metrics. Any other questions? Oh, Pavel?
So increasing the size of spectral libraries is great, but it's also dangerous.
Mm-hmm.
Because the larger is the spectral library, the larger is the chance of misidentifications.
Mm-hmm.
And presumably for every PSM in the spectral library, there is a peptide that matches the spectrum at least as good as the spectrum. As a peptide in spectral library, maybe even better. So how do you deal with this? Or how somebody should deal with this in the future? Because obviously, when spectral library increases, let's say, to millions of spectra, of
everything.
PSM, right, it becomes almost harmful. Because there should be method developed for removing misidentification from spectral library searches.
So So let me ask, so once libraries become, we cover 100% of the proteome. Let's just make a comparison to database search. Database search, you're searching everything in that space, right? In that proteome space. With spectral libraries, you're guaranteed to do better than database search because you don't have to guess the fragmentation. You know the fragmentation. So at least, we should be asking the same problem for database search because there's all these possibilities. And one of the things we can start going forward is because we have all this data of identifications, we know which particular elements in our library we would expect to see more common. So you can assign a prior expectation for observing that particular precursor versus other rare things. And that, if you incorporate that into your score, that might help you in sensitivity.
But this is under the assumption that when you have an element in spectral library, there are no extremely similar peptides in the
okay.
For example, there are no peptides that only differ from each other by a transposition of two consecutive amino acids. This is, of course, correct, let's say, for most of human proteome, but I'm sure incorrect for some if you start looking at short peptides. Right? But this is really is incorrect for natural products. Because in natural products, you often have variants that differ from each other with the same parameters, that differ from each other just very slightly, let's say. Transposition of two amino acids. And in this case, if you don't have the second variant in the library, which is likely, you constantly misidentify the peptide.
So yeah, that is a problem. In the natural product space, if we don't know the space, the full chemical space, then I agree that you're going to have this problem. You don't know the alternatives. You don't know the fragmentation of alternatives. But right now, it's the best we can do. But yeah, this is a good question.
But you actually addressed it.
Did we?
Ambiguity.
Oh, well, so that's if you know the space. But if we don't,
that's the point.
You do. We're assuming.
Space of the human proteome.
Oh, in the human proteome. Yeah.
So he's not asking about natural products. He's asking about proteome.
Okay, yeah. For a particular spectrum, when we do you can do a database search on it, like in our library. We want to remove ambiguity. If there is a swizzle of amino acids, and there's no distinguishing peaks between those two variants, we remove it. So we take the library and we research it, and we define a score cutoff. If there are multiple identifications above that cutoff for a library spectrum, we throw it out. So we avoid those issues.
And what percentage was that?
2% of the data were defined as ambiguous.
So this also emphasizes the dangers of manual annotations, because you can do this and it's great, but somebody who manually does it, manually annotates spectra, will make a mistake.
They can make a mistake. So that's why we need better metrics downstream for checking for these things.
So I always like the comparison between manual and non-manual. So why not keep all the annotations and let the user in the end decide?
That's the current.
You still, let's say you have 3 annotations. In the end, they may look very similar, they may not look very similar, but most of those are going to look very similar. So that's useful information to the end user.
Can a user compute p-values on the back of the envelope?
No. But I can assure you, if somebody who's going to spend 5 years to follow up on that annotation is going to really appreciate having it.
Yeah, I mean, one of the things we kind of punted on this as a library search feature is if you do have multiple spectra that look very, very similar to each other from multiple different compounds, that should be handled at the library search time and say, well, these all look similar giving our score metrics. It's one of these we don't know. We can't distinguish given our scoring criteria. So in our library, we want to make sure whatever is being reported is correct. But if they happen to look similar, that's a question for the library at library search time. So Danny?
you benchmark the identification rates from the spectral libraries in comparison to database search?
So Nuno just asked me that like right before the talk. I don't remember the numbers actually for this particular data set, but as published from the original lab that generated this data, I don't remember at the precursor level, but I think we are maybe 25% increase in identification rates at the PSM level compared to their published results.
Because so one problem I see is you always identify something which was previously identified by database search, correct?
Mm-hmm.
Because the synthetic standards, they're quite a minority, I assume.
They're about 5% of the library, yeah.
Okay, so how do you deal then? There was also like poor annotation coming from the users.
So when we reanalyze, we controlled it very tightly, but that is a good point. Whenever you do database search, there's always error. And so we actually capture that identification error in the libraries. We keep database decoys along with the library. So about 2,000 of the spectra in our library are decoys. And we throw that in with the matching when we do the library search. And if any identification, any spectral match happens between those decoys from the database search, those are also counted as decoys. And it's actually quite interesting when we do this analysis of when we do the identifications, about 0.1% of the library, 0.1% of the library is decoy spectra from the creation step, but 6% of the decoys in library search hit those spectra. So there's this magnification effect there, and we account for that.
And then maybe a very practical question. So for me as a proteomics user, do you think it would be already time to switch from a database search to spectral libraries? For example, if I study something very well studied like the human proteome.
It depends what you're looking for. If you just want to count proteins, definitely go to spectral libraries. If you want to find something new with a new modification, libraries aren't going to help you there.
Okay, so you can't do like spectral proximity search the same way we do with natural products?
We can, but yeah, you will see we had to think about the error rates in those cases. We actually worked on that a couple years ago. And so you lose a lot of sensitivity, but it might work out for you. Yeah, Rob.
Oh, one thing biologists like to do are rarefaction curves. So try to estimate how well we're capturing diversity of whatever we're measuring. So for maybe bacterial 16S sequences, we're getting close to capturing most of the 16S sequences in all the samples we've looked at.
Mm-hmm.
Have you thought about trying to do that for GMPS, like with all of the databases, or all of the databases and all of the samples that have been uploaded? Like how close we're getting to saturating this chemical diversity out there in the biological world?
In terms of the libraries or in terms of mass spectrometry observation?
I guess both, but mostly people running samples.
We have, I guess we've looked at this together in some ways, but I don't think our tool, so this comes down to a clustering problem, a spectral clustering problem. And we've known issues with spectral clustering that do not give us correct assessments of that rarefaction. So we've kind of looked at it incidentally, but we haven't done it in a rigorous fashion.
You mean no, at this scale?
Not at the proteomics scale, but we have done it at the global GMPS, so
Yep.
a couple 100 million spectra. But still, there's problems with the actual clustering that so it won't give us an accurate answer. Yeah, Mike?
So this question comes from Professor Laura Sanchez.
Oh boy.
From the UCSD College of Pharmacy. She says, great job, Ming. What do you think the future of natural products in GMPS will be? In particular, if people continue to contribute, will we find all of the chemistry, or are there still things that we are going to miss?
So, if we look back, okay, there's too many slides, so we're not going to go back. But there's a chart, a graph here.
You can address it to the camera.
Oh, okay, Laura. Of the amount of data that's captured in networks. So I think it'll be pretty easy for us to find networks, identify all the networks, but then there's about 50% of the data that is not in networks. And so it's going to take a substantial effort because they have no correlated fragmentation, and there's just a lot of diversity there for us to actually identify that data. And so I think, yeah, the first couple steps will be relatively simple to annotate maybe 40, 50% of the data, but taking that last step is going to be quite difficult. Yeah.
So I had a couple questions. One is, in your thesis I wasn't really clear when you said covering the proteome.
Okay.
If you meant by one peptide or two peptides per protein, or if you meant every single amino acid sequence you could possibly come up with every single modification that might possibly be there. So what did you mean by that?
So what we meant is just cover for the set of precursors in our library, if we map it to the proteome, that we actually we cover that amino acid. So it doesn't capture all the possible modifications that are known in like Uniprot, but it just says something about, look, we have a sequence and it's observed in this region. We cover amino acid 1, 2, 3, 4, 5, and then we don't cover 6.
Okay. And then how did you deal with modifications in the spectral matching thing?
So with modifications, we search for it with the database search. So we include standard sample handling modifications, some biological modifications. So I think it's 6 or 7. And we rely on the database search to tell us that, tell us that the modifications are there. What we do not guarantee is site localization. So if there's multiple sites, we just say, okay, we pick one of these, we don't assign the specific site, and then we put that into our library. When we do matching, we don't try to say, okay, here's an unmodified version in our library, let's identify a modified version. We just do exact match. And so if we're trying to identify modified peptides, the modified version has to be in the library.
So we still have to do a session with only the committee, so in the interest of time, we'll take maybe one more question. I'll let Ming pick whose hand he's seen the most.
And this is risky, okay.
What you like there's, to my knowledge, there's more than one model of MS spectrometer in the world. How much variance is there between MS2 spectra depending on what make and model it?
Oh boy.
And how do you consider that in your analysis?
So in some cases there's drastic differences in fragmentation. Just comparing like ion trap instruments from Thermo versus Q-top instruments, the fragmentation is quite different. And so for GMPS, we kind of skirt the issue and we just let the matching happen. We presume if the fragmentation is different, well then they'll just have low scores. But if the fragmentation is the same, they'll have high scores. And so we allow users, when they create these libraries, to specify, hey, I collected it on this instrument with some control vocabulary, and then whenever users are analyzing the results, they filter out the results specifically for their input instrument type. And for peptides, you want to start creating libraries specific for an instrument. So we focused here on thermo HCD instruments. But you can think about making libraries for ion trap instruments separately. So it's not ideal currently for GMPS, but it just so happens a lot of our users, at least in the past couple of years, have been running Q-top instruments. They've been uploading Q-top library spectra, and it's been working out.
All right, with that, we finish the general audience part.